All right, so today I'm going to hopefully try to make this as quick as possible. It's a lesson on Extrema using the first derivative test, and it's very similar to what you did with increasing and decreasing functions, only we use the test in a slightly different manner. So here we go. All right, so I have a lot of slides like this, and really I just wanted you to see that, let me move this up a little bit. I wanted you to see that this is what we're going to be calling a relative maximum, and it's a relative maximum because it may not be the maximum of the function. Like for instance, this right-hand side of the graph could be going higher and higher and higher, and the graph itself may actually have no actual maximum value because it might be going to infinity for the y values or down to negative infinity for the y values. So y values are where we get our max and mins, but we look at x values for them. So right here, this is called a relative max because it's relative to the graph. It's a peak, if you will, or a valley is a relative minimum. So those are what we're looking at. So if you go from an increasing to a decreasing, that's going to give you your max, and from a decreasing to an increasing is going to give you your relative minimum. So you can see how we're going to use our knowledge of testing those intervals for increasing versus decreasing to find relative max and mins. And then for this one, it's basically the same thing, but now you've got functions where there may only be one or none. You ought to be able to have a horizontal tangent, which will give you the value of the derivative is going to give you 0. So that means that we would have that horizontal tangent line there, because remember the first derivative is slope. So at that point you would have a slope of 0. And remember at something called a cusp, you really can't have a tangent line because we could draw a tangent line here or here or here. We can draw an infinite number of tangent lines to that point. So they consider the slope, which is your first derivative, at this point undefined. So we're also going to have to find our critical values because the critical values is where those max and mins occur. And then these are the steps that we're going to take, and they're essentially the same steps that we used in the previous lesson for increasing and decreasing. So you are going to find your derivative, and if I were you, I probably wouldn't write any of this down. If you're writing your notes, I would just leave it, so just listen to me. But basically we're going to test intervals, and we're going to look to see based upon those tests, and this is just talking about those intervals, based upon whether the interval is negative or positive, whether or not we have a max or min. So that'll make a little bit more sense as we do some of our problems. And then here's just some visual displays of different types of graphs that you could run into. So as we're testing our intervals, if I've got this relative minimum here, I would imagine that the interval to the left is going to be decreasing, and so you would have a negative value in that first derivative. And then the interval to the right would be increasing, which would mean you'd have a positive value. So if you go from decreasing to increasing, you must have a minimum. If you go from increasing to decreasing, you must have a maximum. And then, of course, sometimes you're going to go here, you've got increasing, more increasing, more increasing, and more increasing. So you've got positives all the way along. There are some functions where you're not going to have a relative max or min. This is still considered a critical value, but it's not a relative max or min because you've got increasing all the way along here. Same thing here. This one's decreasing all the way along here. So there's neither a max nor a min at this critical value right there. All right, so here's example 1, so our first example. So I'm going to shorten up some of my work here, and I did have to make this graph really small for me to be able to get the max and the min in here. But we're going to find our max and mins algebraically. But first we're going to follow the same steps as yesterday. We're going to start with our derivative. Okay, So f prime of x, so this is an easy derivative to find, would be 6x squared minus 6x minus 36. And then our second step is to find our critical values. And so to do that, is I can actually find my critical values without the calculator. So my critical numbers. I'm going to let the derivative equal 0. So I'm going to let f prime of x equal 0, and I'm going to set it equal to this. And then we're going to factor to solve. So I'm going to factor out a 6. And then I'm going to factor the trinomial that's left inside. So the factors of 6 that subtract to give you 1 would be 3 and 2. So x minus 3 and x plus 2. And so then you would set x minus 3 equal to 0 and x plus 2. So my critical numbers are going to occur at x equals 3 and x equals negative 2. Now that doesn't mean that there's a maximum or a minimum there, but you can see here on the graph that we do have a max and a min, so I'll guarantee that they're going to occur here. So the third step is to test our intervals, and the interval testing here really isn't that bad. It's not like it was yesterday. And you're welcome to use your calculator to help you test those intervals. So I'm going to kind of use a table format here. So my intervals, again, I'm going to be splitting this x-axis from negative infinity to positive infinity. And so they're going to be split and cut right here at these values. This is the smaller value out of the two. So I'm going to go from negative infinity to negative 2, from negative 2 to 3, and from 3 to infinity. So I'm going to go okay, so then the values that I'm going to choose, I can choose any value I want to in these intervals. And so we spent a lot of time on the last lesson deciding how to choose. I want to choose as small of a number as possible and an easy number. So in the first interval, I'm going to choose, and you can't choose the endpoints, so I'm going to choose x equals negative 3. In this interval, it's got one of my favorite values to substitute in, which is 0. And on this one, we're going to choose x equals 4. But again, you can choose any values that you want to. So then I'm going to substitute these into the derivative function. So I highly suggest that you take your calculator and you put the derivative, this right here, or this right here, both the same thing, into the y equals of your calculator. And that way you can use the table feature in your calculator to test these values that we're substituting in. So when I substitute in negative 3, I get a value of 36. When I substitute in 0, I get a value of negative 36. And when I substitute in 4, I get a value of positive 36. So this value right here is positive. And what that tells me is that the graph is increasing on this interval. And you can actually see that here, that on the interval from negative infinity until we hit negative 2, that graph is increasing. And then from negative 2 to 3, it's decreasing. And from 3 to positive infinity, it's increasing. So, and that shows up here as well, since this is negative, as we said, it's decreasing. And this one's positive, so that means that the function is increasing. So what we want to do this time, because we're not finding the increasing and decreasing, we're just using that to go a step further. Based upon these right here, if I have an interval that goes from increasing and then to decreasing, I must have hit from increasing to decreasing a maximum value, a peak. If I go from decreasing to increasing, I must have hit a valley or a minimum. So our conclusion is the following. So I'm going to conclude that, therefore, there is, my Vishla is getting very excited over here. She's trying to play with a toy while I'm teaching. No, Liddy, go away. She's now on my lap. Go away. Back off. All right, so, and now the pug wants to play. Pause. Oh, I'm going to pause for a moment. So there must be a relative maximum at x equals -3. And that relative maximum, we will come up with the y value later. But for right now, we just know that there's a relative maximum at the x value of -3 and a relative minimum at x equals, did I say -3? That's supposed to be -2. Let's see if I can erase that. Oh, yeah. Perfect. So that should be x equals -2. The relative minimum is at x equals 3. See what the dogs do to me. They get me off track. All right, so now you try it. Go through the same process that I just did. So pause the video, go through your 3 steps, and then restart the video. All right, so step 1 is going to be our derivative. So f prime of x is equal to 6x squared minus 6. So then step 2, we're going to find our critical numbers. Those are going to help us find our intervals. So that means that I'm going to let f prime of x equals 0, and I am going to factor to solve. So I'm going to start by factoring out a 6, and then factor this as the difference of 2 squares, so x plus 1, x minus 1. If I set those equal to 0, I'm going to have x equaling -1 and x equaling 1. So then step 3 is to test the intervals. All right, so my intervals, the -1 and 1 are going to cut the x-axis. So I'm going to go from -infinity to -1. Then my next interval is going to be from -1 to +1. And then finally from 1 to +infinity. Okay, so the values that we're going to choose in these intervals to test, I'm going to choose, you could have chosen something different, but I'm going to choose -2. What you're looking at is, did you get not the same value as me, but did you get a positive and I got a positive? Did you get a negative and I got a negative? That kind of thing. So here I'm going to choose x equals 0, and here x equals 2. So I'm going to throw those into the first derivative. And the values that I got was 18 when x was -2. I got -6 when x was 0. And I got 18 when x was +2. So my conclusions are, since this is a positive value, the function is increasing on this interval. Since this value is negative, the function is decreasing on this interval, and this value is positive, so the function is increasing. So what you're looking for on the intervals to find a relative max or min is that you go from increasing to decreasing or decreasing to increasing. So because we go from increasing to decreasing, there must be a relative max or min. And so if you envision it, you're going to go increasing means you're going up, and then decreasing means you're going down. So we must have hit a peak, which is a max. Here, decreasing means we're going down, increasing means we're going up, so we must have hit a valley, which is a minimum. And you can see that happening here on this graph as well. So, in conclusion, therefore, there is a relative max at x equals -1 and a relative min at x equals 1. So good job. All right, so in example 2, we have a slightly funkier function. And you can see here in example 2 where there are places like here where there could be a minimum, and here where it looks like something's going on. So on this graph, sometimes we can't always rely on our graph. So that's why it's nice to know what our, sometimes it's nice to use our algebra to get to where we need to be. So I like to use both the graph and my algebra if at all possible. You'll find out in some of these examples we can't always use our algebra. It's more of a pain. So step 1, we're going to find the derivative. So I'm just going to start abbreviating this deriv. So I have f prime of x is equal to, this is pretty simple, 4x cubed minus 3x squared. So then step 2, we're going to find our critical numbers. So that means that we are going to take f prime of x and let that be 0. And we're going to use our algebra to factor and solve. So both of these terms have just an x squared in common, so I'm going to factor that out in front. So I'm left with a 4x minus 3 in parentheses. You're going to set the x squared equal to 0 and the 4x minus 3 equal to 0. Anytime you have a monomial equal to 0, 100% of the time the value of the variable will be 0. So we know that x is equal to 0, and here x is equal to 3/4. So those are our critical numbers, which are going to create our intervals. So we're going to have an interval that goes from -infinity to 0, from 0 to 3/4, and from 3/4 to positive infinity. So step 3, we're going to test those intervals. Okay, so I'm going to start here from -infinity to 0, and we're going to go from 0 to 3/4, and from 3/4 to positive infinity. All right, so the values that I'm going to choose in the intervals, here I'm going to let x equal -1. Here I don't really have much of a choice. I'm just going to let x equal 1/2 because that's a value in between 0 and 3/4. But then on this one, I'm going to let x be positive 1. So I'm going to substitute those into the first derivative. Okay, so now I'm going to use my handy dandy table feature in the calculator. And of course I have put this into the y equals in my calculator. I'm just using the table feature and plugging these values into that table, and it's doing all the work for me. So when I plug -1 in, I get a value of -7. When I substitute in 1/2, I get a value of -1/4. And then for 1, I get a value of 1. All right, so my conclusions would be here I have a negative, so that would be decreasing. Here I have a negative, which means it's still decreasing, so no relative max or min has occurred in between these two values at 0. So as you notice here, it's decreasing, and then it's still decreasing. So there is no relative max or min here. But on the last interval, we have a positive value, which all of a sudden we've gone from decreasing to increasing. So that implies that we have a relative minimum. So therefore, there is a relative minimum at x equals 3/4. And you might want to put a note that there is no relative max or min, because these are your notes. You might want to note that there is no relative max or min at x equals 0. Okay, you try. So pause the video, go through the same process, because it's a very similar example to what I just did, and then restart the video and check your work. All right, so on this, I'm going to move this over a little bit. On this particular graph, I'm going to end up testing values probably here at 0 and here at whatever that value is. So I'm going to use my algebra to help me find that out. So step 1 is my derivative. So f prime of x is equal to 4x cubed minus 12x squared. Step 2, we're going to find our critical numbers. So we are going to let f prime of x be 0, and we will factor and solve. Now both terms have a 4 and an x squared in common. So for the first term I'll have an x left over, and for the second term I'll have a 3. So I'm going to set the 4x squared equal to 0 and the x minus 3 equal to 0. So 4x squared is a monomial, so that means that x has a value of 0, and x minus 3, x has a value of 3. So that helps me find my intervals. So we're going to test those, because remember, this is part of calculus is showing, so you're proving that you're coming up with these. So sorry for all the work, but it is what it is. All right, so test your intervals. The assumption is that we don't actually have use of a calculator, so we can actually do this without a calculator, but I like to look at it since it kind of verifies what I already know. So negative infinity to 0, 0 to 3, and 3 to infinity. All right, so I am choosing x equals -1 here, x equals +1 here, and x equals 4 here. I am going to substitute into the first derivative, for all of these. And when I substitute it in, I've got, now you might not have chosen the same values, remember, so you're just looking for positives and negatives. So I got a -16 for -1, I got a -8 for 1, and I got a +64. So our conclusions, I have a negative here, so that means the function is decreasing. The next interval, I have a negative also, so it again is decreasing, so that means that there is no relative max or min at x equals 0. But here I have a positive value, so the function is increasing. So since I went from decreasing to increasing, I can conclude, therefore, there is a relative minimum at x equals 3. All right, so example 3 has what we call a cusp in the graph. And you can see that the function itself is fun. Let me move it up here. So you can see this cusp here. So this, the value of the first derivative, when we find the first derivative and try to solve for the variable, this is going to be an undefined value because it's a cusp. I can just tell you that right now. Now visually I can see that right here there's probably some sort of a minimum. So I'm looking for there to be perhaps a critical number here and here. So let's look at our math and see where we go from here. So step 1, find the derivative. Okay, so f prime of x. So the first term's derivative, the derivative of 2x, is just 2. Then the derivative of this, you're just going to take 2/3 times -3, which is just -2, and subtract 3/3 from 2/3. So I'm going to get minus 2x to the -1/3. So technically that derivative looks like this. Cube root of x. Now you could put that into one fraction. I don't see any point to it, but from here, this is going to be kind of hard to factor and solve because it's not your normal problem. So from here, I like to look at places of discontinuity, so restrictions. So for instance here, I know that x cannot be 0 because the cube root of 0 is 0, and you cannot have 0 in the denominator. So that is going to create a discontinuity, so that's a critical value because it's undefined. Remember, critical values, when plugged into the derivative, substituted into the derivative, should give you a value of 0 or undefined. So there's an undefined. So x equals 0. Is a critical number because f prime of 0 equals undefined. So based upon our previous work, that should be self-explanatory. And then also, what is going to create 0 in this function is if x is 1. So if I let x be 1, the cube root of 1 is 1. 2 divided by 1 is 2, so 2 minus 2 is 0. And you can kind of see that here in the graph that this value appears to be 1. So that's kind of how I was led to using x equals 1. So that is a critical number because f prime of 1 is equal to 0. All right, so there's our critical values. So I guess that was step 2. I forgot to put that in here. And then step 3, we're going to test our intervals. Okay, so our intervals are going to go from, because we've got 1 and 0 breaking apart, so negative infinity to 0, and then 0 to 1, and then 1 to infinity. Okay, so I am going to choose x equals -1 in this interval. X equals, I'm going to go with 1/2 because I don't have any integers to choose from. And then x equals 2 in this interval. So we're going to substitute into the derivative. Now, when I use the table feature in my calculator, I'm not going to put this in there. I'm going to put this in there. Do make sure that you put this whole parentheses in, or the whole parentheses, the whole exponent in parentheses. So for instance, when you put that into the y equals, that exponent needs to have parentheses around it, just to be on the safe side. And make sure you're using a negative here and not the subtraction, and that you're using subtraction here and not a negative. So put that into your y equals, don't put this one in. So when I put -1 into the function, I got a value of 4. And when I put 1/2 in, I got a lovely decimal, 0.5198. And then I got another lovely decimal here. I mean, don't let the decimals bother you. We're just using them to get positives and negatives. So for this one, we got a positive, so that means the function is increasing. And this one, we got a negative, so that means the function is decreasing. So we went from increasing to decreasing. So that means that we have a relative max. And then here we have a positive. So we went from decreasing to increasing, which does give us a relative minimum. So therefore, so there's a relative max at x equals 0 and a relative min at x equals 1. All right, so you try. This is, again, a very similar example to what I just did. So pause the video and you do your thing and restart the video and check your work. All right, so I expect there to be some relative max and mins there. So step 1, I'm going to find my derivative. So f prime of x is equal to 2x to the -1/3 minus 2, which technically that is written, so it looks like this, 2 over the cube root of x minus 2, and only write it that way so that I can look for points of discontinuity. So I know for a fact that here there's going to be a point of discontinuity at x equals 0 because that will create, so that is a critical number because I know that if I plug or substitute the value of 0 into the derivative, I'm going to get an undefined value. So automatically, that is a critical number. And then also based upon the work we did in the previous problem, I know that if I substitute in 1 for x, that will also be a critical number because if I substitute 1 into the function, it will give me a value of 0. Don't believe me? Try it. So then step 3, you're going to test your intervals. All right, so my intervals are going to go from -∞ to 0, from 0 to 1, and from 1 to positive infinity. And then I'm going to choose x equals -1, x equals 1/2, and x equals 2, and I will substitute those into the first derivative. Okay, so remember that I am putting this into the y equals of my calculator, and also I made sure to put parentheses around the -1/3 as well. So when I plugged those into my calculator, I got the following values of -4, Making sure I'm on the same problem as you. Yes, good. -1/4, and then I got a lovely decimal, 0.51984. And then for this one, -0.4126. And it's not about the numbers, it's about the signs. So on this one, I have a negative, so the function is decreasing. This one, I have a positive, so the function is increasing. That creates, going from a negative or a decreasing to an increasing, that creates a relative minimum. And then this one is negative, so it's decreasing. So we went from increasing to decreasing, which is a relative maximum. So therefore, there is a relative minimum. Whoops, handwriting's terrible. Relative minimum at x equals 0, whoops, equals, and a relative maximum at x equals 1. All right, so then for this one, it's just, again, I wouldn't write this down if you're handwriting your notes at all, but for our purposes here, we are going to find absolute max and mins on an interval. And so we're going to do some additional testing, but it's going to be slightly different. So we're just going to look at part of a function, not an entire function, and just look at that part of the function. So for instance, look at this next slide here. This is just showing part of a function going from some number a to some number b. So we're just going to look at that part and look for relative max and minimums within that function. So although the steps are nearly identical, the testings and conclusions are slightly different. So let's watch to see how that changes things. So again, these are just some guidelines. I wouldn't necessarily write this down if you're taking all the notes by hand. So we're going to evaluate the function at each of the critical values and at the endpoints. And so even though something's not a critical value, it could end up being a maximum. Here we go. Look at example 4. So for example 4, we are going to look for max and minimum values only from an x value of 0 to 5. So on the interval 0 to 5 implies we're going from an x value of 0 to 5. So on our function, so I'm going to highlight the parts of the function that represents. Maybe I'll use a blue highlighter. Let me get my width smaller. All right, so that would represent the area of this curve from here to here only. That is where the function's x values of 0, there's the y value at 0, all the way to x value of 5, there's the y value at 5. So that means on the curve, we're just looking at this part of the curve. So this right here is going to end up being a maximum, even though it's not a critical value, a critical number. This is going to be a relative minimum, and it is a critical number. And then this is going to be neither, because it's not going to be the highest point on this curve or the lowest. So look at our steps. So step 1, here comes Avishla wanting to play. Terrific. Step 1. We still are finding the derivative. All right, so f prime of x is equal to 2x minus 6. So pretty simple. And we are going to find our critical numbers just like we did before. We're going to use our algebra. Because we need those critical numbers for our interval. So I'm going to let f prime of x be 0, and we're going to solve for x. So I've got 2x is equal to 6. I added 6 to both sides and divide by 2. I get x is equal to 3. So we're only going to have 2 intervals because we only have one cut. We're cutting the x-axis here at 3. So we're going to go from 0 to 3 and from 3 to 5. So we're not going to have negative infinity and positive infinity, not an interval. So you're going to start one interval with this endpoint. So we're going to go from 0 to 3. And then from 3, we're going to finish up at the next endpoint, 5. So here we go. So step 3. You are going to test your endpoints and your critical number. So our test is going to look a little bit different. So we're going to have an endpoint, and we're going to let that endpoint be x equals 0. And then we're going to have a critical number. And that critical number we just found is x equals 3. So you can see that we're not really kind of doing an interval. I'm going to actually test each of the endpoints and test directly at the critical number. And then the other endpoint is x equals 5. So we are not going to plug into the derivative. We are going to substitute into the original function. So we are not subbing into the derivative. We are subbing into the original function. That's a 5. My 5s are looking terrible today, sorry. All right, so I am putting this into the y equals of my calculator and using the table feature to quicken up my math. And so when I substitute 0 into the function, I get a value of 2. When I substitute negative 7 into or 3 into the function, I get a value of negative 7. And when I substitute 5 into the function, I get a value of negative 3. So my conclusions are, I'm going to look at these 3 values and which one's the highest and which one's the lowest. So this is the highest value out of the 3 numbers. So this is my relative max. This is my lowest value, so that's my relative min. So we're just going to call them max and mins at this point. And this is neither the highest nor the lowest. So my conclusions are going to be, so this one was my highest value, so I have a max. And you're going to see my answer is going to look different. I have a max at x equals 2 at x equals 0 of 2. So my max occurs at the x value of 0, and the value of the maximum is 2. That's why we substituted into the original function, because that gives us the actual value of the maximum at that critical number. But we needed the derivative to help us find that critical number. All right, so then this is going to be our minimum. So we have a min at x equals 3 of negative 7. And then this one is neither max or min. I'm going to extend these a little bit. And that's it. That's all there is to it. So then we have one last problem for you to do on your own. All right, so you try this problem, and you are going to find the max and min on the interval 0 to 7. So pause the video, find your derivative, find your critical number, test at your endpoint, your critical number, and your other endpoint, and then make your conclusions. So restart the video when you're ready. Okay, so step 1. Derivative is f prime of x is equal to 2 2x minus 8. Then step 2, you're finding your critical number. So we are going to let the derivative equal 0 and solve for x. So if we add 8 to both sides and divide by 2, we get x equals 4. And so then step 3 is to test your endpoints and your critical number. So I have an endpoint. So my first endpoint is at 0. So I'm going to test x equals 0. And then I have a critical number. And that critical number we just found was x equals 4. And then my final endpoint is at x equals 7. Okay, so then we are going to substitute into the original function, not the derivative. So your answers should match my answers. And again, I use the table feature in my calculator. I put this original into the y equals and let it do the math for me. So when I substitute in 0, I got 10. When I substituted in 4, I got -6. And when I substituted in 7, I got 3. So then you evaluate these numbers. 10 is the highest and -6 is the lowest. So this is our maximum, this is our minimum, and this is neither. So the conclusion is that there is a max at x equals 0 of 10. And for here we have a min at x equals 4 of -6. And then this is neither a max or a min. And that's it. Pretty simple stuff this week.